All right, so in this video, we're going to start looking at chemical reactions, and you can see throughout the chapter, we're going to look at various aspects of chemical reactions, including balancing them, so making sure that we have the same amount of matter on both sides of a reaction. Classifying them, so we're going to see several different types of reactions. And then the last few are going to be kind of the math of chemical reactions with stoichiometry, thinking about how much of a reactant do we need to get a certain amount of a desired product, or if we have a certain amount of product produced, how much of the reactant was used in that case. So we're going to be able to relate different substances in a chemical reaction. Reaction yields, kind of just looking at the efficiency of a chemical reaction, and then several different types of analysis of these reactions and just different substances at some points. But with this, we're going to see chemical reactions are occurring around us daily, constantly. If we're thinking about even just like charging a phone, that's going to be considered a chemical reaction. You can see an example here, the fuel source for a rocket, similar to the fuel source just in your car, vehicle, bus, whatever you're taking to get around. I guess as long as it's not a bike. With it, it's going to be a different type of fuel. But in each case, we're going to be looking at a combustion reaction. So we're going to be producing energy from that chemical reaction. And when we're writing these chemical reactions, there's going to be different forms we can have. So we'll see the molecular reaction is kind of the most common. That's showing what the reactants are, what are we starting with, and then what are we ultimately producing. But we're going to see the total ionic and the net ionic equation is going to give us a little bit more detail in some cases in terms of what's really occurring in those chemical reactions. But with this, when we're looking at any of those different types of reactions in terms of how can we write them, or when we're looking at any of the different classifications of reactions, or the different types of reactions in terms of like combustion, decomposition, whatever it may be, the thing that they're all going to have in common is that they're going to be balanced in the sense that whatever we start that reaction with, we're going to be finishing with the same amount of stuff. We're just going to be taking those original atoms, breaking bonds, reforming new ones. So we're going to be taking those atoms and essentially just rearranging them. But the amount of matter that we start with is going to be what we finish with. And that's just referring to the law of conservation of mass. And then with these equations as well, we're typically going to be thinking of them as chemical equations. So we're going to be taking those substances and actually changing their identity, creating an entirely new substance, or multiple substances, depending on the type of reaction. But we can also use the equation sort of format to represent physical changes as well. So if we're thinking about like a process like boiling or any phase change, it's going to be the same substance on both sides. So we'll have the same chemical formula, but we'll have a different subscript, because with these chemical equations, we're going to see the formulas are going to be important. Making sure they're balanced is going to be important, but we're also going to want to make sure we specify for those reactants and products what type of or what state of matter is that in, because the state of matter can have big consequences in terms of will the reaction actually work or not. In some cases, how fast or how slow is the reaction going to go? Is there a certain way we need to set up that reaction in order to perform it safely, depending on the state of matter? So that detail is going to be an important piece of these equations as well. But when we're thinking about balancing it, if we just look at a simple combustion reaction, so in this case, this is going to be methane, CH4, so the primary component in natural gas. So when we're looking at when we're using the Bunsen burners in labs, for instance, we're going to be burning methane. But in that reaction, we're taking that methane molecule and reacting it with oxygen to produce carbon dioxide and water. But if we just had CH4, O2, CO2, and H2O, we're not going to have the same amount of things on each side. So if we just had one of each of these, we're going to have two oxygens on the left, but then we'll have two oxygens and carbon dioxide. We'll have a third oxygen and water. So we need to add these coefficients in order to make sure that the reaction's balanced. So when we're balancing a chemical reaction, just note, we can't change anything about the formula themselves. So we can't change anything about CH4 or O2, CO2, H2O, whatever it may be for that particular reaction. But what we can do is come and add these coefficients in front. And now what this is saying is 1 molecule of methane plus 2 molecules of oxygen is going to react to produce 1 molecule of carbon dioxide and then 2 molecules of water. And then when we look at it in this case, we've got 4 of these red oxygens on the left, 2 in carbon dioxide, 2 more from the 2 water molecules. So we've got 4 oxygens on the right. We've got 4 hydrogens now from the 2 water molecules. We have 4 hydrogens in that methane, and then we just have a single carbon on each side. So now with these coefficients, we're satisfying the law of conservation of mass. We're taking the same amount of stuff, finishing the reaction with that same amount of stuff. We're just rearranging it into something new. And then just in general, just a couple of kind of basic points about these chemical equations when we're writing them out. We're going to have the reactants on the left. So if we're thinking about just the way that you read a book or the way you read anything on this slide, we go left to right. So we're going to do the same thing with the chemical reactions. So we're starting with whatever those reactants may be on the left. And then if we've got multiple reactants, we're going to separate them with a plus sign. So that's why here we've got methane and oxygen separated by this plus sign. So it's telling us both of these are reactants, but they're 2 different substances. If we just had CH4O2 and had that all matched together, then that would be telling us it's just one substance. So we separate them with a plus sign. And then we've got an arrow pointed to the right, which is telling us we're going to take these substances and then convert them into the products. So the products are going to be what we finish that reaction with. And again, if we've got multiple of these products, we'll separate them with the plus sign. And then the numbers out in front, so if we go back here, the 2 in front of oxygen, the 2 in front of water, those are just known as the coefficients. And those are going to be how we balance these chemical reactions. So remember, when we're balancing them, we can only add the coefficients out in front. We can't change the formulas themselves. And with it, we don't need to write in the one. So like with methane here, CH4, we don't have to write C1H4. That one's just implied unless there's another number there. It's going to be the same with the coefficients. If you want to write in the 1 in front of CH4 or the 1 in front of CO2, you can do that. It's not incorrect, but it's just implied to be 1 if there's no value there. But then if we've got multiple, like we've got 2 oxygens, 2 water, we need to specify in that case exactly how many of those we have. And with the balanced equation, we're always going to use, and we'll see how we can kind of go through this and balance these. But when we're balancing these reactions, we're always going to do it so that the coefficients are the simplest whole numbers. So the important thing is, 1, we want whole numbers there. So if we're thinking about them as molecules, for instance, we can't have half of a molecule of a substance, and that would just be an entirely different substance. So we want whole numbers, and we want to have them in the simplest ratio. So when you're balancing a reaction, if you get coefficients in front of everything, just double check to make sure that those can't be reduced any further. If you have a coefficient in 1 in front of anything, that can't be reduced, and nothing else is going to be able to be reduced. But if you do have coefficients in front of things, just see if they could be reduced further. Because if we think about the reaction that we just saw, the coefficients were 1, 2, 1, 2. So it would still also be balanced if we had 2, 4, 2, 4, or 3, 6, 3, 6. In each of those cases, we would still have the same amount of matter on both sides of the reaction. We'd still have the same number of carbon, hydrogen, and oxygen on both sides, but it just wouldn't be the simplest ratio, so it technically wouldn't be 100% correct in that case. And the reason we just use the simplest coefficients is just because no matter what, it's always going to be in that same ratio. And with it, when we're looking at the oxygen atoms, for instance, in the previous one, we had 1 CO2, 2 water molecules. So the reason that there was 4 oxygens total is because each of these carbon dioxide molecules were giving us 2 oxygen atoms, but we only had 1 of the carbon dioxide. And then each of these water molecules gave us 1 oxygen, but we have 2 of those molecules. So we're getting 2 of them from the single carbon dioxide. We're getting 2 of them from each of the water molecules combined. So we've got 4 total there. Okay. So now if we look at a example here, so we've got the decomposition of water. So we'll see when we take one substance and just break it down into smaller pieces, that's going to be known as a decomposition reaction. But when we look at this reaction, we've got 2 hydrogens on the left. We've got 2 hydrogens on the right, but we've only got a single oxygen on the left. We've got 2 oxygens on the right. So when you're going to balance these reactions, I would recommend making a little bit of a table like this. Sometimes I just do HO or whatever the elements are. So HO on the left, HO on the right, just so we can keep track of everything. And then, like we said, we've got 2 hydrogens, 1 oxygen on the left, 2 hydrogens, 2 oxygens on the right. So as you go through this, you're going to have to start adding the coefficients in front of some of these substances. And depending on the reaction, we may have to kind of go back and forth. So we might have to add a coefficient to one side, and then that may mess up something on the other. So we have to kind of go back and forth and add coefficients in a few different places. But as long as you have your table and as long as you're kind of updating it as you add those coefficients, you'll always be able to keep track of exactly what you have. So you can always see where you're at, where do we need to add something else. And for this one, if we think about it, hydrogen's already balanced, so we don't need to worry about that. But we've got 1 oxygen on the left, we've got 2 of them on the right. So we need to increase the number on the left. So what we're going to do then is just come here and put a 2 there. What that's going to do now is give us 2 of these water molecules. So now we've got 2 of the oxygens on both sides. And it looks like our table is balanced now, 2 and 2, 2 and 2. But when we add this coefficient in front of water, whenever you add a coefficient in front of everything, you're going to change the number of the element that you were focused on. So in this case, the oxygen, but it's also going to change the number of every other element in that substance. So we're also going to change the number of hydrogen. We're going to wind up doubling that as well. So now we've got 4 hydrogens, because we're getting 2 of them per water molecule, and we've got 2 of those water molecules. We're getting 2 oxygens. So we fixed the oxygen, but then we messed up the hydrogen. So now we've got to go back to the product side and just put a 2 in front of hydrogen as well. That'll give us a 4th on that side too. So with this one, like I said, we're going to have to go back and forth. But as long as you update your table, and then again, make sure you're updating the table for every element in that formula. So when we added the coefficient in front of water, I was focused on oxygen. But since we also have hydrogen there, that's going to change as well. But as long as you keep updating your table and just keep going back and forth how you need to, this process is always just going to be the same. And then again, with these balancing steps, we can never change the substance itself. So we can't add the subscripts at all. So if we go back here, I can't come in and add a 2 after the oxygen, because if I did that, it would balance the reaction. But now we're no longer looking at the decomposition of water, then we'd be looking at the decomposition of hydrogen peroxide, which is an entirely different substance. So when we're balancing these, we can only add those coefficients out in front of the different chemical formulas. We can't change the formulas themselves. So actually, with this one, it's already kind of balanced. But if we don't think about the coefficients here at all, the way we could kind of work through this and go from the unbalanced to this form is if you look at it, we've got 2 carbons on the left. But with carbon dioxide, we only have 1. So that's why we have to put a 2 there. And then we've got 6 hydrogens on the left. Only have hydrogen and water. We're only getting 2 of those though. So we need 3 of those water molecules then to get 6 hydrogens on both sides. And then when we do that, now we've got 3 oxygens coming from the 3 water molecules. We've got 4 oxygens coming from the 2 carbon dioxides. So we've got 7 oxygens total. We only have oxygen and O2 on the left-hand side. So if we think about what times 2 is going to give us 7 in terms of the coefficient out in front, we're going to wind up with 7 halves or 3.5. It's 3.5, 7 halves times 2 is just going to give us 7. And the reason we can do this is just kind of, or the reason we do this is kind of just as a shortcut, because this allows us to technically have it balanced. We've got 2 carbons on both sides, we've got 6 hydrogens, we've got 7 oxygens, but with this 7 halves, we can't have half of an oxygen molecule. In that case, it would just be a lone oxygen atom, which is an entirely different substance. So then what we do is take this chemical equation and just multiply the entire thing by 2, because by doing that, that'll make the oxygen coefficient just 7. And then we'll have to scale up everything else to keep it balanced. So we'll wind up with a 2 in front of the ethane, 7 in front of oxygen. So that 2 should be a subscript. It just didn't get put as the tiny 2. We'll wind up with 6 waters instead of 3. We'll wind up with 4 carbon dioxides instead of 2. But now if we look at this reaction, 2 carbons per ethane molecule, but we've got 2 of those molecules, so we've got 4 carbons total. Each carbon dioxide gives us 1, but we've got 4 of them, so we've got 4 carbons on both sides. 6 hydrogens per molecule, but we've got 2 molecules, so we've got 12 hydrogens. 2 hydrogens per water, but we've got 6 molecules, so again, we've got 12 hydrogens on both sides. And then we've got 14 of these oxygen atoms now. We're getting 6 from water. We're getting 8 more from carbon dioxide, so 6 plus 8 just gives us 14. So we still have the reaction balanced, and now we've got it in terms of the simplest whole number coefficients. Because with 2, 6, and 4, we would be able to reduce those. But since we have that 7, nothing's going to go evenly into all 3 of those values. And then, like I mentioned as well, the final kind of piece of these equations. So we've got the formula. We've got the chemical formula for each substance. We need that formula to be correct. Otherwise, we're looking at the incorrect reaction. We need the coefficients in order to balance it. But then with the final piece, we're looking at the state of matter. So with each of these reactants, we want to specify, is it a solid, a liquid, a gas? A lot of the times we'll have something dissolved into the solution. So a lot of the times we'll see this AQ subscript for aqueous. So that just means we took that substance and dissolved it in water. And you can dissolve things in many other solvents than just water. But that's just the easiest, the most common one. So if we had it dissolved in like an organic solvent or something, typically it would specify what that solvent actually is. But with water, since it's so common, we just have the abbreviation AQ. And just note, AQ is very different than liquid. Both of them are in the solution is going to be liquid. And then, of course, a liquid will be liquid. But the difference between the L and the AQ is that the L is referring to a pure substance. So it means we took that substance and either heated it up above the melting point, turned it into a liquid, or we cooled it down below the boiling point, made it a liquid. But it's that pure substance. So in this case, it's just pure water or pure whatever it may be. Whereas AQ means we just took that substance and dissolved it in water. So for sodium hydroxide, for instance, in this case, we could take some of the sodium hydroxide pellets. We will have it go through this reaction, but if we wanted to just make this solution, we could take some sodium hydroxide pellets, just add them to water, have them dissolve, and then we'll make that solution. Whereas if we wanted to make sodium hydroxide liquid, we would then have to take that sodium hydroxide, heat it up a whole bunch, and actually melt it. So those are going to be 2 very different substances, and we'd have to handle them very differently as well. So that's why it's going to be important that we specify what state of matter we're going to have for these substances. But again, if we look at it, we still have this one balanced. 2 sodiums on both sides, 4 hydrogens on the left. We get 2 hydrogens from the sodium hydroxides. We get 2 more from the hydrogen molecule. So we've got 4 there. 2 oxygens. We're getting 2 oxygens from both of those sodium hydroxide molecules combined. So we still have it balanced. And then in some cases, like with the decomposition of calcium carbonate, we don't even need coefficients to balance it. So again, just note some of these values aren't getting subscripted. But we've got 1 calcium on each side. We've got 1 carbon on each side, 3 oxygens on the left. And then we've got the oxygens split up in this case, but we still have 3 of them total. But with these, just note there is also some other notation that can sometimes be included in the chemical reaction or the chemical equation. In this case, if we just had calcium carbonate, which is a pretty common component of antacids, so it's going to help neutralize stomach acid. But if we just had that calcium carbonate and essentially just kind of let it sit on the table or desk, whatever, it's not just going to spontaneously turn into calcium oxide and carbon dioxide. So what we've got to do is heat this substance up. And if we heat it up enough, then we can actually break those bonds, have it decompose into those 2 other substances. So in order to indicate that we need to heat this reaction, we just use the triangle. We use the delta symbol above the arrow to represent the addition of heat in order for this reaction to occur. And then similarly, sometimes, so if we think about this as thermal energy, kind of breaking this substance down, we can see similar reactions caused by light. So if you have the correct wavelength of light, in some cases, it can be enough to break down a substance. And in that case, instead of the delta symbol above the arrow, what we use to represent that, what we use to represent the photons, or the energy of the photons that are breaking down whatever that substance may be, we would have HV. So if you think about hydrogen peroxide, for instance, H2O2, and that might be, that's the next one. All right. So if we think about hydrogen peroxide, H2O2, you might have it in your bathroom cabinet, just because you can use it to disinfect cuts and things like that. But with it, it's typically stored in a brown bottle, just because that's going to help prevent light from getting in. And that light can actually break down the hydrogen peroxide, so we can actually break it down into just water and then oxygen gas. So with that reaction, instead of having the delta symbol over it, we would just have the H, and then is it new? That weird V with the line coming off the left side. And what that represents is just the energy of a photon. So we can calculate the energy of a photon. We'll learn about this in a later chapter by using Planck's constant H, and then just the wavelength, or the frequency rather. We could use the wavelength, but we'd have to alter the equation slightly. So that HV looking thing, which I think is new, but again, I can never remember the Greek letters, just represents the energy of a photon, whereas you can think of the delta symbol as representing the thermal energy that comes from actually heating that particular reaction. And then also in some cases, just to mention, sometimes it'll say cat or catalyst above the arrow, or it'll actually specify a particular substance that's acting as a catalyst. We'll learn about those later when we look at sort of the speed of reactions and things that affect that. But a catalyst is just going to be something that speeds up a reaction, but we don't actually consider it to be a reactant or a product, because it winds up returning to the same form after the reaction. So it might kind of change throughout, but we're going to be able to get that same catalyst out at the end of the reaction as we started with. But as I mentioned, we've got a couple of different ways we can kind of write these chemical formulas, particularly when we're looking at reactions in solution. We've got the molecular equation, which is the most common, just shows exactly what all of those chemical formulas are going to be. But when we've got these substances in solution, what we have is no longer calcium and 2 chlorides actually combined, or a silver with a nitrate actually combined, or calcium with 2 nitrates on the right-hand side. What we're going to have is these ionic substances actually dissociating. So water actually kind of rips those molecules apart, and then we get positive ions and negative ions, and then the water molecules essentially just surround those. So for calcium chloride, for instance, we'd wind up with a calcium 2+ ion, 2+ because it's in group 2, but because it's positive, those water molecules are essentially just going to surround it, so the negative oxygen of water is closer to that calcium. And then the chloride is just the opposite. It's got a -1 charge. So the water molecules are still going to surround it, but it's going to surround it so that the positive hydrogens are pointed at the chlorine. And the same thing for these other ionic substances that are aqueous. So with the total ionic or the net ionic equation, we're going to actually see what these substances would really be acting like. Because like I said, it's not going to be this intact molecule anymore. We're going to get those individual ions dissociating. So with the different ionic equations, we're going to get a better representation of what those solutions really look like. If we could kind of see what the substances are, we'll no longer have these intact molecules. But just note with the solids, so in this case, we'll see it's a precipitation reaction. With the solids, they actually are going to stay together. So the silver and the chlorine in this case are going to stay joined together. So we won't break that one apart. We'll only do it for the aqueous ionic substances. And with these substances, like I said, going to break down as those individual ions. So just note with the polyatomic ions like nitrate, it doesn't split into nitrogen and oxygen ions. We still just keep that nitrate ion as one whole thing, but we're going to separate the negative and the positive pieces from each other. And the coefficient of 2 in front of silver nitrate just comes from this balanced chemical equation. But if we look at any of these individually, we'll note that we still have the same amount of atoms on each side, or ions on the right. So we've got 1 calcium, we've got 2 chlorines, and then also note we still have a balance of charge. So on the left-hand side, all of these are neutral formulas, but on the right, we've got a positive and negative, but we've got a positive 2 with 2 negative 1s, 2 positive 1s with 2 negative 1s, positive 2 with 2 negative 1s. So we still have that balance of both mass and charge. But what we're seeing on the right-hand side is what these solutions would actually be behaving as. We'd have a calcium ion and 2 chlorines separate from one another, or 2 silvers and 2 nitrates, rather than 2 whole silver nitrate molecules. So with these ionic equations, we're going to be better representing what these solutions actually are. But again, with the silver chloride, we don't break that one apart because it's insoluble, we'll see. So it stays as a solid, so we'll still have the silver and the chloride actually combined there. So with the complete, or I typically call it the total ionic equation, what we're seeing in this case is what everything looks like in that chemical reaction. So for the reactants on the left, both of those are aqueous solutions. So both of them are going to separate into those individual ions. So we've got calcium 2+ with 2 chloride ions. And we can think about this as one beaker beforehand. And then the same thing, we've got the 2 silver ions with the 2 nitrates. That would be another beaker. So in those solutions, we're going to have those separate ions just kind of swimming around. But then when we take these 2 beakers together, we mix them together rather, we're going to have all of these jumbled up now. And we'll still have an attraction between calcium and chloride because we've got opposite charges there. But that's an aqueous solution that's going to be soluble. So even if those kind of meet up, they're going to quickly separate, stay as those individual ions. Same thing if silver and nitrate bounce around and come together. But when we've got all of these mixed together now, we'll also have an attraction between calcium and nitrate. But we can see here that's an aqueous solution. So those are going to stay dissolved. They're going to stay separate from one another still. They won't form that solid. But now when a silver and a chloride bump into each other, those are going to be insoluble together. This is going to be why we'll actually form a precipitate. So we'll actually see a solid form in this one. And this will be one of the types of reactions we focus on. But with the silver chloride, now those ions are going to stay together. And that's why we're forming a solid. And that's why in this ionic equation, we're keeping those together as one whole substance, whereas everything else, we're still keeping as the individual ions. And with this, if we had a reaction on a quiz or a test or something, and we needed to identify which of these is going to be an insoluble product, we're going to have a solubility table. So we won't have to memorize kind of the rules for solubility. We would just want to recognize if silver chlorides are our precipitate, it's going to be the solid then. And we're going to keep it as the molecular formula rather than splitting it into the individual ions like these aqueous solutions will dissociate into. But if we look at this now, so this is the complete ionic equation because it's showing us everything we'll have in those beakers. But now if we look at the reaction, on the left-hand side, we've got calcium 2+, that's aqueous. We have the same thing on the right. We've got 2 nitrates that are aqueous on the left. Same thing on the right-hand side. So with the calcium and the nitrate, they're not really changing at all. They're essentially just kind of watching this reaction occur. So those are going to be what are known as spectator ions. And what we can do is take this complete or total ionic equation, remove those spectator ions from it, and then just have the net ionic equation. So the one that's actually just showing kind of what's changing throughout this process. So in this case, if we remove the calcium and the nitrate from both sides, now we're just going to have a silver ion, a chloride ion coming together to form silver chloride. So again, with the spectator ions, in this case, calcium and nitrate, those are going to be the things that are exactly the same on both sides of the reaction. So they stay as an aqueous solution. And because of that, they're not changing. So with the net ionic equation, if you think about like when you're working, you've got your gross pay, which is just your hourly wage times however many hours you work. But then you've got your net pay, which is how much you actually take home after taxes and whatever else. So with the net ionic equation, we're kind of thinking about that as what's actually changing from the left to the right, rather than all of the things that are present there. All right, and with this, we'll continue to look at that type of reaction. So it's going to be known as precipitation reaction, going to be focused on solubility. But then we'll also talk about acid-base reactions and redox reactions. And through this, we'll talk about acids and bases, just the general basics of them, as well as oxidation states and solubility guidelines. Okay. So with the first one here, like we just saw, precipitation reaction, this is going to be where we actually take two solutions and mix them together just to form a solid product or products. And sometimes these are more generally known as double displacement, double replacement, metathesis. I would generally call them double replacement just because that's the term that I use the most out of those three. But if we're looking at specifically two aqueous solutions producing a solid, that's going to be a specific precipitation reaction. And with these, it's just going to be based on the solubility of those two different substances. So like we just saw with the previous one, we had two ionic substances. So we had calcium chloride and silver nitrate. So we had positive and negative ions. And essentially what's happening in that case is we're taking the positive ions from both of those substances and just switching what they're associated with. And in that process, we're changing those substances. So we're going to be changing the solubility. And solubility is just a measure of how well does something dissolve. So if something has a larger or higher solubility, just means we can dissolve more of it in that given solvent. So if you think about if we had 100 grams of water, we could take some amount of salt and dissolve it in there. But eventually we're going to hit a point where it no longer dissolves. It just sinks to the bottom. The amount of salt we added to reach that point is just going to be the solubility. So it's a measure of how much of that solute, so the substance we're dissolving, can dissolve in a given amount of solvent. But with some of these substances, when we change those ions, when we change those identities, we're going to be changing that solubility into something that's going to be known as insoluble. And with it just means we can only dissolve a very, very tiny amount. So typically you'll still be able to dissolve a very, very minor amount, but most of that substance is going to stay essentially undissolved. So with these precipitation reactions, we're just going to be creating an insoluble precipitate. We're going to be creating an insoluble solid. And that's why with them, it can sometimes be a little bit hard to recognize that it's a solid, just because we still do have a lot of solution mixed in there. So we still have a lot of other solution mixed in, kind of spreading out that solid. So sometimes it's a little bit harder to see. But with these ones in lab, we had one with lead, and that might even be an example we look at here. Yeah. So we had an example with lead that gave us a really nice yellow precipitate. And in that case, we just took two colorless solutions, mixed them together. But when we did that, when we switched what the ions were with, we formed an insoluble precipitate, and that's why we formed that yellow solid. And like I said, with these ones, we're going to have a list of solubility rules, so you don't have to memorize these. We would just have to know how to use this. And I give you a little bit different of a table that I think is a little bit easier to understand, but it's essentially kind of the same information. It's showing us, in this case, soluble compounds contain group 1 metal cations. So pretty much anything with something like sodium or potassium is always going to dissolve. And the same thing, the ammonium ion, NH4+. So pretty much no matter what cation anion, excuse me, that we have with those things, so whatever the negative piece is, we'll pretty much always see those dissolve. Same thing if we take a group 17 ion, so chlorine, fluorine, bromine, iodine, whatever it may be. Typically, those are going to dissolve, except for if we combine them with one of these exceptions. And that's just kind of how we can use this table. This stuff up here in the top left is going to be stuff that'll typically dissolve, except for a couple of these exceptions. And then the stuff at the bottom here, stuff that typically won't dissolve, except for when we take them and combine them with these. So like the hydroxide ion, we're going to talk about when we look at bases, but the hydroxide ion typically going to have very, very low solubility, except for if we put it with a group 1 metal or barium. And then the same thing with carbonate, chromate, phosphates, or sulfide, typically not going to dissolve very well, except for if we put it with one of those group 1 metals or the ammonium ion. And again, that's why we're seeing up here, there's really no exceptions for group 1 or the ammonium ion, just because those are always going to dissolve very, very well. Okay, but this is the reaction we saw in lab with that nice yellow precipitate. So we took a potassium iodide solution, Ki, and mixed it with a lead-2 nitrate solution, PbNO3 in parentheses 2. And when we did that, we're now switching the lead and the iodide. So with this, if we needed to predict the products, what we want to do, so we wouldn't have the 2 here already, we would just have Ki and PbNO3 2. We wouldn't want to just take these pieces and mash them together, so we wouldn't just want to do K and then NO3 in parentheses 2 or PbI, because we still have these as ions. We're just switching what they're with, so they're still going to have the same charges. So in the potassium iodide, K plus, I minus. But then in the lead-2 nitrate, I'm telling you it's lead-2 nitrate, so that's telling us it's lead-2. But if we didn't know the name of it already, each of these nitrates is going to be -1. So that means the lead has to be +2 to balance it out. So then when we go to form the product here, we're going to have PbI2 now combining with that I minus. So if lead is giving up 2 electrons, but iodine can only take 1, that's why we're going to need a second iodide in this product. And then with the potassium nitrate, K plus, and then the nitrate ion, we can look at the polyatomic ion list to see that it's -1. So if we got K plus, NO3 minus, we just need 1 of each of those. And then in order to balance it, we've got 2 iodines on the right. We need a second potassium iodide to give us that second iodine then. But that gives us 2 potassiums then. So we've got to go back to the right and just put a 2 in front of KNO3. And if we also didn't know which of these products is soluble or not, we could go back here. Potassium's a group 1 metal cation, no exception, so we can be confident that the potassium nitrate is going to dissolve. Same thing with the nitrate, no exceptions. So both of those pieces are going to have very good solubility together. But then with the other product, that lead-2 iodide, the halide ion, something like iodide, typically going to be soluble. But now lead-2 plus is one of those exceptions. So that's why we're seeing this as the solid precipitate there. But now if we think about going from the molecular equation down to this net ionic equation, we would separate this out into those different ions. So we'd have 2K plus, we'd have 2I minus, Pb2 plus, 2NO3 minus, because all of these are aqueous. And then the same thing with the potassium nitrate, we'd have 2K plus, 2NO3 minus. But because the lead-2 iodide is a solid, we're just going to keep this exactly as it is as we went to the total ionic equation. So then when we get to the net ionic equation, nothing's changing about the potassium or the nitrate. Those start as aqueous, finish as aqueous. So we're going to remove those from our equation and now just focus on the lead and the iodine. And again, if we look at it, 1 lead on each side, 2 iodides, 2 plus, 1 minus, but we've got 2 of them. So we've got a neutral charge overall on the left. This formula is neutral overall on the right. So we still have a balance of charge and mass here. And then, like I said, with this one, this is the one where we see that nice yellow color forming. In this case, it looks a little bit more kind of crystally than the one that we had, but it's still that same substance. And then if we look at one more here, again, sodium chloride. So that one pretty easy to know that'll be aqueous just because you can always take salt, just throw it in some water and it'll dissolve. But silver nitrate again, as the other piece there. And then when we mix them, silver and chlorine, so if you think about it, positive, going to go with the negative piece of the other, positive, going to go with the negative piece of the other. So sodium nitrate, group 1, and nitrate, both of those are going to be very soluble, AQ. But then chloride, silver is going to be one of the exceptions for its solubility. So that's why we're seeing it stay as a solid. And in this case, we don't need any coefficients in order to balance it. So when we get to the net ionic equation, the only thing that's changing is the things that are going to form this solid. So it's just going to be that silver, which is always +1, along with the chlorine, that'll be -1 because it wants to gain 1 more electron to fill its valence shell. And that's why we're just seeing silver chloride as the only substance in that net ionic equation on the product side. There. And then with the next reaction, we're going to be looking at an acid-base reaction. So first we need to talk about what an acid or a base is. And an acid is just going to be something that increases the concentration of hydronium ions. So when we take an acid and add it to water, we're going to be making H3O plus. With this, just also note H plus is the exact same thing. And with it, it's kind of just thinking about how we're looking at that reaction. Because in this case, we're considering water to kind of be a reactant itself. So water is taking the hydrogen ion from the HCl to form H3O plus, and then we've just got that negative chloride to keep everything balanced in terms of mass and charge. But we could also write this reaction where water is kind of just above the arrow. And in that case, we'll still have that chloride ion. But what we're going to show in that case, instead of H3O plus, is just the hydrogen ion itself. Oops. Sorry for the plus sign there. So we could also just have that where H2O is above the arrow, and then we're seeing the hydrochloric acid dissociate into that H plus and the Cl minus. And that's why with the pH scale, just the negative log or negative log of the hydrogen ion concentration, or the negative log of the hydronium ion concentration. That'll be something that we look at more when we look at the chapter of acids and bases specifically, but we're just going to look at the general pieces here. So let me clear that. And I typically just do the H plus rather than the hydronium ion, but again, they are the exact same thing. But when we look at hydrochloric acid, we've used this acid in lab before. This is going to be known as a strong acid, and we'll see the difference between strong and weak. Both of them we have to handle with care, but there's the difference in terms how do they kind of react with water. But one thing we can notice with the acid here, and we'll see with the other acids we look at as well, is we're going to have that hydrogen at the front of the formula. And with these acids, they're going to donate that hydrogen ion. So when we get to acids and bases, that chapter, we'll see there's actually a few definitions for acids and bases that are slightly different depending on what type of acid or base we want to kind of, or what sort of lens we want to look at it through. But they're all going to be similar in the sense that acids are going to increase the amount of H plus we have. And with it, we're going to consider HCl to be considered a strong acid because 100% of this substance is going to dissociate into the hydrogen or the hydronium ion and that negative chloride. With the weak acids, we'll see we'll only get a little bit of that dissociation, so we're only going to get a little bit more of that H plus. And with it, hydrochloric acid won't be the only strong acid. There's going to be a handful of them. But again, the thing that will be similar about all of them is that molecule is going to completely break down into H plus or hydronium, depending on how you want to think about it, and then whatever that negative portion is going to be. So when we look at all of these strong acids, the thing that's going to be the same about them is we'll no longer have HBr as an intact molecule, or HCl, HI, HNO3, HClO4, H2SO4, whatever it is. We're going to see these hydrogens and then that negative portion are all going to dissociate similar to the ionic compounds. And then because they completely dissociate, that's why we're considering them to be strong. With the weak acids, we're going to see they'll kind of look the same. They'll do the same thing, but rather than completely dissociating, giving us 100% of those ions, the weak acids are only going to partially dissociate, so we'll only get a little bit of that H plus, and then whatever the negative piece of that particular acid is. But all of these are strong, so all of them are going to completely dissociate, and by dissociate, I just mean separate out from the positive hydrogen, and then the negative bromine or the negative chloride, negative nitrate, whatever it may be for that particular acid. But as I mentioned, there are a lot of weak acids, which will do kind of the same thing, just to a lesser degree. So they're still going to increase the H plus, the hydronium ion concentration when we dissolve them in water. But it's only going to go up a little bit rather than completely dissociating. So in this case, we're looking at acetic acid, and this is just a little bit of a different form. Normally, you'd have the hydrogen out at the front, but it's the same thing. And what we're seeing in this case is we're still reacting it with water. We're still getting a negative ion we're still getting that positive hydronium. But just note, in this case, we've got the double arrow. So with the previous one with HCl, we had an arrow pointing from left to right. In this case, we've got arrows pointing in both directions, because what we're going to see here is we've got what's known as an equilibrium being reached. So rather than taking all of those reactants and converting them into products, we get to a point where this reaction sort of essentially stops. The reason we have a double arrow is because we still have a reaction. We're still taking these reactants, converting them into the products, but the arrow pointing to the left is then telling us we're also taking some of these products and converting them back into the reactants. So because we reach that point where both of those processes going left to right or right to left are occurring at the same speed now, it seems like nothing's happening. So that's what I mean by the reaction stopped. We still have it going in both of those directions, but if it's going at the same speed in both, and we think about it as kind of a scoreboard keeping track of everything on the left and the right, nothing on that scoreboard would change any longer. So with the acetic acid, so that's going to be the primary component in vinegar, the component in vinegar that gives it smell, at least, not the primary component. We'll see of this molecule, some of it will break down into these ions, but only about 1% of it will do that. So we're going to have 99% of this substance still staying as that intact molecule. So that's why we're only getting a little bit of that hydronium or the hydrogen ion, and that's why we're considering this to be a weak acid. Still could be dangerous with vinegar. You don't really need to worry about it. But with glacial acetic acid, which is just very, very concentrated acetic acid, that's still going to be dangerous. So that's still going to be something that we need to handle with care. So just because something's a weak acid, and we'll see the same thing with bases, just with the OH ion, just because they're considered weak acids or weak bases, doesn't mean that they're harmless. Doesn't mean that we don't need to be careful when we're using them. It just means that they don't dissociate fully, but they still could be very dangerous to work with. So we would still want to make sure we got our eyewear on, still have goggles and whatever other protective equipment we may need. And with these weak acids, these are going to be fairly common. So if you think about your stomach acid, for instance, that's primarily hydrochloric acid, I believe. So it's going to be a strong acid. But when we're looking at different foods and different beverages and things like that, a lot of those are going to contain weak acids. And that's why sometimes people with digestive issues, with stomach issues, ulcers and things like that, may need to avoid certain foods, just because the acidity of those foods can then further complicate whatever those problems may be. But when we're looking at fruit especially, those are going to contain, in some cases, citric acid. So if we're thinking about citrus fruit, citric acid, kind of makes sense that they have the same kind of name there. Vinegar, as I mentioned, going to contain acetic acid. But then also with the fruit, vitamin C is just going to be ascorbic acid. And again, it's going to be a weak acid because it'll increase the hydrogen ion concentration, but it's not going to fully dissociate. So we only get a little bit of that hydrogen ion. But when we're looking at acids and bases, acids, of course, are just going to be one half of that equation. The other half is going to be base. And one of the reasons I like to think of acids as H plus rather than the hydronium ion, and again, they're the same thing, is because then when we think about water, H2O, we could rewrite it as HOH. So when we look at the water then, we've got H plus for the acid, and then the other piece there is just going to be the OH minus for the base. So we're going to see that water, when we talk about acids and bases, can actually act as an acid or a base, just because it's going to have both of those pieces. But now when we look at the examples of the bases, so with the acids, we're kind of looking for that H plus, or that hydrogen at the front of the formula as kind of an indicator that it'll be an acid. With the bases, we're looking for something similar. It's just now we're looking for the hydroxide ion at the end of it. So we've got stuff like sodium hydroxide, potassium hydroxide, calcium, barium hydroxide, whatever it may be. We'll see in the next slide or one after that, we'll see that it doesn't necessarily need to have hydroxide in the formula. because there's other ways to increase the hydroxide ion concentration. But with the bases, we're just going to increase that OH minus concentration when we dissolve that substance in solution. And just like with the acids, a strong base just means that the substance is going to completely dissociate. So with something like sodium hydroxide or potassium hydroxide, it's going to completely separate into sodium ions and hydroxide ions, or potassium and hydroxide ions, whereas the weak bases still going to give us some of that hydroxide ion concentration, but most of it would stay as that intact molecule. So we can see the example of sodium hydroxide here, and it makes sense why sodium hydroxide or potassium hydroxide would be a strong base, why it would completely dissociate, because those are going to be group 1 metal cations that are going to be very soluble with pretty much everything, including hydroxide, even though hydroxide itself is typically lower in solubility. So we're going to see sodium hydroxide, and that's again why we've got the single arrow. So we've only got it pointed in one direction, because we're going to have 100% of this substance dissociate into those individual ions. Whereas with a weak base, something like ammonia, so this is an example of a base that doesn't actually have hydroxide in the formula, but the reason that this is going to be considered a base is because when we have it react with water, it's essentially going to take one of those hydrogens from water and then form the ammonium ion, NH4+. So if we take the H from the water, now that's just leaving us with the OH minus. So we're still increasing that hydroxide ion concentration. But we're just not getting 100% of the ions like we would with sodium hydroxide. So the weak strong part is the same with acids and bases. It's just whether we're looking at the H plus or the hydronium ion for acids, or the hydroxide ion for the bases. And with these bases, they're going to be used in cleaning products commonly. So bases typically have kind of a slippery feel to them, and that's why they're white cleaning products also feel slippery, because they contain those bases a lot. And with it, I wouldn't really use ammonia as a cleaner in the house, just because one, it's just kind of burns your nose if you smell it. But then also it's can be dangerous. So if you're ever using cleaners, never mix them. Or at least double check that they're safe to mix, because depending on what the cleaner is, if you mix ammonia with specific other types of cleaning products, you can actually produce, depending on what you're mixing together, you can produce different types of gases that can be very, very toxic, if not lethal. So with the cleaning products, just make sure you never mix them together. But then we also see ammonia used in agriculture, so primarily in fertilizer. And that's going to be important if we think about food production. So we have a growing population, so we need to produce more and more food in order to feed everybody. But with that use of fertilizer, there's going to be nitrogen in there, which can then run off. So if you think about fertilizer in the field, it then rains, or we water the crops, whatever it may be, that water can then run off the field and then get into waterways, so it can get into lakes and ponds and streams and whatever else. So with the nitrogen, as well as phosphorus, are important nutrients for plants. But if those then run off into the water, they can cause algae blooms, which will essentially just coat the top of water with kind of a green slime. So I think about a month or two ago, one of the largest lakes in Ireland was currently experiencing something like this, where it was basically just covered in inches of kind of green muck. And that's got a couple consequences. One, just from a purely sort of selfish standpoint as humans, it just prevents people from then using that lake for recreational reasons, so swimming, boating, fishing, whatever it may be. But then if we think about the organisms that are actually living in that body of water, when the algae coats the top of it, it's then going to prevent sunlight from getting through. So it's going to prevent the plants that are living in that body of water from performing photosynthesis. So ultimately, those plants will die. And then photosynthesis, one of the products is going to be oxygen. So that dissolved oxygen is going to be important for all of the fish or other aquatic life living in water. So then if the oxygen supply is no longer being replenished, as those organisms perform respiration, the oxygen concentration is just going to, the dissolved oxygen concentration is just going to continue to decrease and decrease further. And eventually it gets to a point where there's not enough oxygen for those organisms to live. So they're either going to need to try to move away, find some other area in either the lake or the river, go upstream, whatever it may be. Otherwise, just like the plants, they'll no longer be able to survive. So with fertilizer, similar to pesticides even, they're going to be important. They're going to be very useful tools in terms of agriculture and growing crops. But we got to make sure that we're using them properly, because they're going to have extremely damaging negative consequences if we're not careful. But with the acids and the bases, when we take those two together, this is going to be known as an acid-base neutralization reaction. And the reason we consider it to be a neutralization reaction is because we're taking, if we have them in the right quantities, of course, if we have a ton of base and just a little acid, we're not going to be able to fully neutralize them. But if we had just the right amounts of those two substances, we've got an acid that's going to be a low pH. We've got a base that's going to be a high pH. But when we mix them together, we're essentially just going to be creating salt water. So salt is just a term for any ionic substance. So in this case, it's magnesium chloride, doesn't have to be table salt. But we're producing salt water. So low pH, high pH, and then water just going to be a neutral pH. So that's why they're known as that neutralization reaction. And with it, if we kind of look at what's happening here, again, I talked about water can act as an acid or a base. So we've got the H from the acid, the OH minus from the base. So those are just coming together to form the water. And then the salt piece, we're just taking the positive piece from the base, the negative piece from the acid, and combining those. And then since magnesium's +2, chloride's -1, that's why we wind up with the formula MgCl2. So we've got to add in a couple coefficients in order for it to balance out. But this is going to be the general formula we'll see for all of these acid-base reactions. We're going to take an acid and a base and just create salt water. Depending on what the acid and the base are in particular, that'll determine exactly what salt we produce. But the general structure for these types of reactions is what we're seeing up top here. So what you can see here is going to be a acid-base reaction. So I don't particularly like seafood, and I'm allergic to some of it, so I don't know exactly the specifics of this, if there's anything else you need to kind of do with it in order to prepare it. But I do know they sometimes use acid, so something like citrus acid or the vinegar, acetic acid. They sometimes use that to essentially kind of cook fish and things like that, because what happens here is we're taking whatever that acid may be. So again, citric acid, acetic acid, whatever it is, that weak acid, and we're reacting it with the base that's actually in the fish itself, just to create these new substances. So with this one, you can see hydrogen getting transferred to that base. So with this one, the reaction looks a little bit different, just because we're not really showing the water at all in here. But when we look at acids and bases, we'll see again the different types of definitions for acids and bases, and we'll look at more specific types of reactions for these. But for now, we just want to essentially remember this piece up here. So acids plus base give us salt water. And then the final type of reaction that we're going to look at is going to be redox reactions, and we'll actually see there's going to be different types of redox reactions, so we can kind of further classify these. But the term redox just comes from oxidation reduction. And oxidation reduction are going to be two separate processes, but they're going to occur simultaneously. And what they involve is just the transfer of electrons. So if something's gaining electrons, we'll learn that that's reduction. Something else has to then be losing those electrons. They can't just appear out of nowhere or disappear into some vacuum and go away forever. So we need these processes to occur simultaneously. So if something's losing electrons, something else has to be gaining those, and vice versa. And with it, because we're going to have the transfer of electrons there, we're going to see that something known as oxidation numbers or oxidation states are going to change as well. And with those, we'll see how we can kind of assign those oxidation numbers. For ionic substances, it's just exactly what the charge is on that given element. With covalent substances, it represents something slightly different, but it's going to be kind of the same process. So we'll see how we can work those out. But if we just look at what's happening here, we've got sodium metal, so that pure sodium, chlorine gas, pure chlorine, forming sodium chloride. So if we think about the sodium chloride, it's going to be Na plus and Cl minus. But with these reactions, if we focus on each of those individually, if we split them into half reactions, so there'll also be a chapter later on where we kind of focus on electrochemistry. We'll focus more on these types of half reactions. Today, we're just going to kind of get the general gist of them. But if we focus on these elements in terms of half reactions, so only look at sodium and only look at chlorine, we'd have Na going to Na plus. And then we've got the 2's just from the balance reaction itself. So we've got 2 sodiums on each side. But in terms of the charge, on the left, it's neutral. On the right, we've got a positive 2 charge overall because each of these sodiums is +1. So in order to balance this reaction then, we need 2 more negative pieces on the right. So we need to add 2 electrons there. And that makes sense because each of these sodiums is then losing 1 electron. But we've got 2 of the sodiums, so they're giving up 2 electrons total. And then for the chlorine piece, it's kind of just the opposite. We've got Cl2 going to 2 chloride ions. So now we've got a negative charge on the right. We need to get a negative charge on the left then in order to balance it. So we need to add those 2 electrons. And again, that makes sense because each of these is going from a neutral chlorine to a chlorine with a -1 charge. So each of these chlorines is taking on 1 extra electron. And now that we have this transfer of electrons, we're going to see that the sodium is being oxidized, the chlorine then is being reduced. And that's why we've called them oxidation reduction reactions. We have those 2 processes occurring in tandem. All right. So as I said, sodium is being oxidized, chlorine is being reduced. And with this, there's a couple different ways you can remember this. I'm not going to write it just because I guess I can put it in the one of the oops. So I'm just doing the I lowercase just so it's easier to tell that it's not a lowercase L or anything. But one way to remember this is oil rig. So oil stands for oxidation is loss. And then the second piece stands for reduction is gain. So we're thinking about electrons because remember, those are what's involved in bonding. Those are what's involved in chemical reactions. So if we're losing an electron, like with oxidation, we're losing an electron, we're losing a negative piece, we're going to see the oxidized substance is going to become more positive. And then reduction, just the opposite. If we're gaining an electron, we're gaining a negative piece, we're going to become more negative. And then a similar way to remember it. So Leo the lion, I think has something to do with like astrology or whatever. But Leo says gur, so he like growls or whatever you want to think of it as. But Leo, losing electrons is oxidation. And again, if we're losing electrons, we're losing a negative, we're going to become more positive. And then the gur part, gaining electrons is reduction. We're gaining electrons, we're gaining a negative, we're going to become more negative ourselves. Or that substances, I should say. So there's a couple of different ways we can kind of remember what these processes are. But if you also just think about reduction in general, anytime we reduce something, we decrease it. So with reduction, we're going to see the oxidation number for that substance is going to decrease. It's going to become more negative. It's going to go down. And in order for that to occur, we need to take on more negative pieces. We need to gain more of those electrons. So with these 2 processes, they're just going to be the opposite of one another. So if you can remember one of them, you can then remember the other one because it's just going to be the opposite. So oxidation, we're going to see it's going to become more positive because it's losing electrons. Reduction, it's going to go down because it's gaining those electrons. And then a little bit of terminology here. So this is sometimes a little bit confusing because it's kind of backwards almost. But the substance that's getting oxidized, so in this case, the sodium, would be known as the reducing agent or the reductant. And the way you can think about that is because it's causing the reducing, or with the chlorine, that's the substance that's being reduced. So we're going to refer to that as the oxidizing agent or the oxidant, because it's the one that causes sodium to be oxidized. So it's a little bit backwards, but if you can just remember that the agent piece is going to be the opposite of what's actually happening to that. The reduced species is going to be the oxidizing agent. The oxidized species would be the reducing agent. And again, that's just a little bit of terminology we'll use here. And with the ionic substances, like I said, the oxidation number or oxidation state, synonymous terms, but with ionic substances, those represent the charge exactly. With covalent substances, we don't actually have charges because they're sharing the electrons. So what we think of the oxidation number for covalent substances as is what would the charge be on those elements if they were to be ionic. So if we look at something like the reaction here, we can see why it's going to be considered a oxidation reduction reaction, even though it's not going to be a reaction that actually involves the transfer of electrons. But we'll see when we look at the rules in a couple of slides for oxidation numbers. If it's a pure element and it's neutral, it's going to have an oxidation number of 0. So on the reactant side, hydrogen gas, chlorine gas, both just those pure elements, so it doesn't matter that we have 2 of them. If you think about it as an ionic substance, it'd be weird if one of those hydrogens transfer the electrons to the other. They're going to be exactly the same. So with these pure elements, they're going to have an oxidation number of 0. But now on the product side, if this was to be an ionic substance, chlorine's more electronegative than hydrogen. So what we're going to see is hydrogen would lose its 1 electron, become positive. Chlorine going to gain that same electron, become negative. And now that we're seeing the oxidation number for both of those substances change, we're going to consider this to be a redox reaction. So in this case, hydrogen's becoming more positive. Hydrogen is being oxidized, meaning hydrogen's the reducing agent. And chlorine's just the opposite. Chlorine's going from 0 to -1. So chlorine itself is being reduced, making chlorine the oxidizing agent. But like I said, we're going to look at a few rules for assigning these oxidation numbers. The first one, just like we saw, if it's a pure element and it's neutral, the oxidation number is just going to be 0. So if it's sodium metal, just Na by itself, if it's a diatomic molecule, O2, F2, Cl2, N2, H2, any of those, even if we have more of them, so phosphorus is P4, sulfur is S8, whatever it is, if it's that pure element and it's neutral overall, the oxidation number is going to be 0. But then if it's a monatomic ion, so if we think about something like fluoride, F-, the oxidation number is just going to be -1. Na plus would just be +1. If we think about calcium 2+, that would be equal to +2. So if it's just that 1 ion by itself, the oxidation number is just going to be directly equal to whatever that charge is. So aluminum 3+ would have a +3 oxidation number. Oxygen, group 16, typically going to be -2. So if it's just that one thing by itself, whatever that charge is going to be the oxidation number. And then with these elements, we've got a few rules. So it's not on here, but group 1, metal, always going to be +1. Group 2 group 2 metal, always going to be +2. Aluminum, always going to be +3 in a compound. I should say for all 3 of those. So group 1 in a compound +1, group 2 in a compound +2, aluminum in a compound +3. If it's just that individual metal by itself, neutral, it'll be 0. But in compounds, those will always be 1, 2, and 3 respectively. But with the non-metals, and even with the transition metals, we can have different numbers there. So we've got different rules for some of them. And then some of these pieces we'll see a few examples with. We've got to kind of do a little bit of math to figure out what they are. But hydrogen is always either in a compound. So again, with any of these, if it's just that pure element, it'll be 0. But in a compound, hydrogen's either going to be plus or minus 1. And it'll just depend on what type of elements it's with. So with the nonmetals, just like we just saw with the hydrogen chloride, with the nonmetals, since the nonmetals themselves are going to want to gain electrons, hydrogen then is going to be positive, so it'll just be positive 1. And then with metals, so if we think about something like sodium hydride, NaH, sodium wants to be plus 1. So in that case, hydrogen is just going to be negative 1. So depending on which type of element we have hydrogen with, that'll determine if it's plus or minus 1. Oxygen in a compound, pretty much always going to be negative 2. So if we think about water, for instance, H2O, in that case, hydrogen is with oxygen, which is a nonmetal. So each of those hydrogens would be plus 1. So then that oxygen is going to be negative 2. It's going to be able to balance out both of those hydrogens. So oxygen for the vast majority of compounds is going to be negative 2. There are a few exceptions with that. So the peroxides, so if we think about H2O2, in that case, with the peroxides, oxygen will be negative 1. Superperoxides, which we'll never really see, which are just very, very reactive substances, is going to be negative 1/2. So it's going to be pretty unstable. That's why they're going to be so reactive. But what we will see is in some cases, if we have it with fluorine, then it's going to be some positive value depending on exactly what else we have it with. So if you think about OF2, oxygen difluoride, we'll see here fluorine is always negative 1. So if we've got 2 of those fluorines, we really got a negative 2 overall, and it's got to balance out to neutral since it's a neutral compound. So in that case, oxygen would be plus 2. But that's going to be a pretty rare situation there. So for the most part, oxygen is always going to be negative 2 in compounds. And then the reason oxygen will be positive with fluorine, and the reason that fluorine is always going to be negative 1, is because with these covalent substances, again, we don't really have charges, but we're thinking about what the charges would be if there was a full transfer of electrons. Fluorine is going to be the only element that's more electronegative than oxygen. So fluorine is essentially the only element that can kind of overpower oxygen and would be able to take electrons from oxygen. So that's why in that case, oxygen would be positive, and then fluorine will only be negative 1, just because it only needs 1 extra valence electron in order to fill its valence shell. The rest of the halogens similarly would also be negative 1 for the most part, except for if we combine them with oxygen or fluorine, just because those are going to be more electronegative. So those will be able to overpower those lower halogens as well. And then the last one is just whatever the sum of those oxidation numbers are for every atom or ion in a substance. The sum of those oxidation numbers has to match the charge of that substance. So if it's a neutral compound, the sum of those oxidation numbers have to balance out to 0. So that's like with water, each hydrogen's plus 1 gives us positive 2, but oxygen's negative 2. So it balances out to 0. But with the ions, now we'll have a charge. So the sum of those oxidation numbers for a polyatomic ion just has to balance out to whatever that charge actually is. So instead of balancing out to 0, if it's a sulfate ion, SO4 2-, the sum of the oxidation numbers for that sulfur and those 4 oxygens would just have to add up to negative 2. And we'll see a few examples. But if we look at hydrogen sulfide, for instance, H2S, we can kind of just work through this. We've got to figure out what sulfur is. So with some of these nonmetals, things that aren't oxygen or fluorine or the other halogens, depending on if they're not with oxygen or fluorine, those we've got to do kind of a little bit of math to actually figure out what they are. And it's going to be a similar process to when we were figuring out what's the charge on a transition metal in a given ionic compound. We're going to know what everything has to balance out to. Just got to balance out to neutral if it's a neutral compound, or whatever that charge is if it's a polyatomic ion. And then with it, we're always going to have enough information about all of the other elements. So in this case, we've got hydrogen and sulfur. We know what hydrogen is going to be. So we're just missing sulfur. We're just missing that one piece. We're going to be able to solve for that one. So since H2S is neutral overall, the sum of these oxidation numbers has to balance out to 0. And since hydrogen is with a non-metal in sulfur, hydrogen's got to be +1. So with this, we can just kind of look at the setup here, set up a little bit of algebra. It's got to equal 0, just because this compound is neutral overall. And then we've got 2 hydrogens that are each +1. So we've got 2 + 1. And then we're just representing 1x for that single sulfur there. If we had 3 sulfurs, that wouldn't really work for this formula. But if we did have 3 sulfurs, then we would just have 3x in that case. But since we just have the 1 sulfur, we've just got 1x. And then I usually just use the symbol for that element as the variable. But you can use x, you can use whatever you want. But if this has to balance out to 0, and we're getting a +2 from those hydrogens collectively, that means the missing sulfur piece just has to be -2 in that case. So with any of these, if we're looking for the oxidation number, it's just going to be at most doing a little bit of algebra if it's not something that we went over one of those rules for. So again, if we look at sulfur, in this case, we're looking at the sulfite ion, so SO3 with a -2 charge. So in this case, everything has to balance out to -2. But we know what oxygen is going to be. So we've got 3 of those oxygens that are each going to be -2. And then we're still just missing 1 sulfur. So if it's got to balance out to -2, and we've got a -6 from these oxygens, that means that sulfur, if we solve for the algebra, is just going to be a +4 there. If this was sulfur trioxide and it was a neutral molecule, then it would add up to 0. So we'd see in that case sulfur would be +6. But in this case, with the sulfite ion, only needs to balance out to -2. So we only need sulfur to be a +4. And with one like this, there's a couple ways we could solve for the sulfur in sodium sulfate. So in this case, we've got Na2SO4. When we've got a polyatomic ion, we can just focus on that ion. So we could do SO4 2-, and then just basically work through everything we just did with the sulfite. It's just in this case, we've got an additional oxygen, so we've got an extra -2. So that's why the sulfur in this case would be +6. But we could do the same thing with this entire molecule here. So Na2SO4, if we're focused on the entire molecule, though, it's not going to balance out to -2. It would balance out to 0. So we'd have 2 times 1, because sodium's +1, because it's group 1. We've got sulfur missing, so that's our variable. And then we've got 4 oxygens that are each -2. So we've got a +2 and a -8 from the oxygen. So we've got a -6 from those 2 elements. This entire thing has to balance out to 0. So if sodium and oxygen combine to be -6, again, sulfur would just have to be +6. So we can either focus on the entire compound, or if it's part of the polyatomic ion, we can just look at that polyatomic ion specifically. It's just if you do focus on the ion, even though this entire thing is neutral, if you do focus on just the ion, it's got to balance out to the charge of that ion. So we just want to make sure that we're considering what pieces we're actually looking at. And like I said, with the oxidation reduction, we're going to see oxidation lose electrons. Oxidation number is going to increase then. Reduction, just the opposite. So when we're looking at a chemical reaction, what we can do is assign the oxidation numbers and actually see what changes. So let me get the pen. And some of these we don't have to do any math for. So we've got 0, 0. Hydrogen will be plus. Oxygen will be -2. Chlorine will be -1. Aluminum will be +3. So some of these we can just use the rules to kind of assign. And then with these, just note the oxidation numbers may look like they don't match up. So +3, -2, of course, doesn't balance out to 0 because this is a neutral compound. But we've got 2 of these aluminums that are each +3. We've got 3 of these oxygens that are each -2. So we've got a +6, -6, and then kind of the same thing with the rest of these. But now with the ammonium chlorate, or perchlorate. In this case, we've got a couple different elements: nitrogen, hydrogen, chlorine, and oxygen. So with the oxygen, we can be confident that that'll be -2, hydrogen, going to be +1. And then this has to add up to 0 because it's a neutral compound. But we've got two missing pieces here. So in this case, what we would want to do is split this in half and focus on each of these ions individually. So what I'll do is so for the NH4 plus ammonium, that first piece of it has to add up to +1 just because ammonium is going to be positive. We've got nitrogen, and then we've got 4 hydrogens that are each +1. So with it, if we solve for this one, we're going to see nitrogen is -3, and that's probably going to throw everything off. So nitrogen will have to be -3. And then we can do the same thing. The perchlorate ion is going to be -1, so it's got to balance out to -1. We've got that single chlorine, but then we've got 4 oxygens that are each going to be -2. So when we go through and solve for this one, chlorine is just going to have to be +7. So we've got -3. +7. And with this, we can double check that works out because we've got -3, +4, +7, -8 really. So with the -8 from oxygen, -3 from nitrogen gives us -11 overall. +4 from the hydrogens, +7 from chlorine gives us +11. So we've got a balance between positive and negative there. And this is a neutral compound, so everything balances out to 0. So then with the next piece here, we've got to look at what's being oxidized, what's being reduced. I'll do oxidation in blue. We look at aluminum. Oops. We look at aluminum going 0 to +3. So it's in 2 different compounds on the right-hand side, but in each case, it has an oxidation number of 0 to +3. So it's losing those electrons, becoming more positive. And then if we look at nitrogen as well, going -3 all the way to 0. So it's also becoming more positive, losing electrons. And then with I'll use red for reduction. With the other piece here, if we look hydrogen +1 to +1, so this is going to be kind of a weird reaction because we do have 2 species being oxidized. But if we're just looking to see what's being oxidized, what's being reduced, hydrogen +1 on the other side, oxygen -2, stays as -2 in each of those products. But then with the chlorine, +7 to -1. So chlorine's decreasing a whole bunch here. So chlorine would just be our reduced piece. So again, with these oxidation reductions, we'll focus on it more in a later chapter. There's going to be a piece where we can actually kind of balance these reactions, looking at the half reaction. So focusing on what's being oxidized, focus on what's being reduced. So we'll see these when we look at electrochemistry. But for now, we're just looking to see, is it a redox reaction? Are those oxidation numbers changing? And then this is going to be specifically a combustion reaction. So you can see it's the example of solid rocket fuel. So this is kind of a more unique combustion reaction, because typically with combustion reactions, we're thinking about burning it in the presence of oxygen. Not the case here, but it's still going to be a combustion reaction because it's going to be used as a fuel source essentially, and we're producing a lot of heat. in the form of flame along with light. But with these combustion reactions, they're always going to be examples of redox reactions. So we're always going to see something being oxidized. We're always going to be something getting reduced. In this case, we've got multiple elements being oxidized and just a single element being reduced, but we're still seeing those oxidation numbers change. And that's why we're considering it to be a redox reaction. Just erase this before going to the next slide. And then another type of reaction that'll always be a redox reaction is going to be known as a single replacement reaction. So just remember, with the precipitation, those were double replacement because we had two ionic compounds and we were essentially just switching one of the elements, or one of the positive ions with each other. In this case, with the single replacement reactions, what we're going to see is we're going to have a compound plus a element, and we're essentially just going to have that element replace something in that compound. So in this case, we start with copper and a compound, and then we're finishing with copper in that compound and silver by itself. But this would be an example of a redox reaction because copper is going to be 0 on the left, and then in the nitrate compound, it's going to be +2 in order to balance out those two nitrates. And then silver, going to be +1 in that initial reactant, going to wind up being neutral or having an oxidation number of 0 in the product. So with this reaction, if we look at it, it's kind of hard to see, but with the test tube here, we've got a colorless solution. That's just going to be the silver nitrate. So it's going to have the +1 silver ions, those NO3 ions as well. And then we've got the copper wire. We can then take that wire, place it in solution, and what we're going to see is the aluminum, or not the aluminum, the silver and the copper essentially swap places. So the reason that this solution becomes blue then is because now we're getting those copper ions in solution. You look, CuNO3 AQ. So the copper is going to be in solution as the copper 2+, and then the nitrate will be separate. But because those copper ions are colored blue in solution, that's why we see the solution turn that color. Kind of got a little bit of a green tint to it, maybe, depending on, or maybe that's just me. But then if you also look at the metal, you're seeing it kind of looks, in some cases, almost kind of fluffy, but you're definitely seeing it become darker, changing, because now we're actually replacing that metal with the solid silver. And that's why we've got silver just as S here. So remember, with the transition metals, most of them give us these types of colored solutions, but some of them, like zinc and silver, just are colorless. I think iron sometimes has a little bit of a yellow tint to it, but that one usually also mostly colorless, at least at lower concentrations. And this was a longer video, so I'll stop here. And then with the second half of this chapter, we're going to look at kind of the mathematics of chemical reactions.